All right, good afternoon. It is my privilege to introduce Professor Dan Baker, today's Colloquium speaker. Professor Baker started his academic career at the University of Iowa, working with Van Allen, who is one of the fathers of space physics. He had a small period at Caltech, working with another hero of space physics, the Voyager project manager, or principal scientist, and then moved to Los Alamos, then Goddard, and for the last 3 decades, he is the director of the Laboratory for Atmospheric and Space Physics. During his directorship, the lab has grown tremendously, but beyond the fact that the size is much bigger, we have tremendous new capabilities scientifically and technically as well. Dan has a tremendous vita. I just tell you that the table of contents is 6 pages long.
Large print, though.
he had one. He's a member of multiple academies. He's a fellow of the AGU. He's probably one of the founding fathers of the subject of today's talk about space weather. Please welcome Professor Baker.
Thank you for your kind remarks. Founding father, huh? Okay. Got something to live up to. Yeah, good afternoon. Thank you all for being here. And I'm going to talk about the subject of space weather. I'm going to spend quite a bit of time introducing what space weather is to maybe help understand why we want to predict its variability. And I'll start by just saying that the study of the space environment, space physics, has sort of 2 branches. Go turn around a little bit here. One branch is the more scientific, the basic research branch, to understand the sun and its interaction with interplanetary medium and Earth particularly. Then getting an understanding of that, we can extend that to comparing with other planetary systems, for example, and extending the understanding we get of space plasma processes to the universe beyond. And so that's a fascinating and worthy topic on its own. The other branch of this is the more applied branch, and the effects of the sun and the space environment on humans in space, on the operation of spacecraft, of ground-based systems and space-based systems involving communication and power, and even the possible effects on the Earth's climate are all the topic, more the topic of today's conversation. So when you talk about terrestrial weather, there have been a lot of important people who have made important comments about that. Oscar Wilde said conversation about weather is the last refuge of the unimaginative. It's probably true of space weather in a sense too. Ken Hubbard, American humorist, said, "Don't knock the weather." 9/10 of the people couldn't start a conversation if it didn't change once in a while, and that's certainly one of the things about space weather is that it changes, and when it does, it can have important consequences. There have been various definitions. I'm going to be talking about natural space weather, I guess you could say. There's another branch that is probably worthy of conversation at some future colloquium, and that's more the anthropogenic space weather, what we're doing to change the environment around our planet and beyond. But the natural space weather sort of starts with the sun and talks about the effects on the various technological systems, as you can read there. And I'll be addressing a number of these and telling you about some of the things we know have occurred and likely will occur. So we'll start with what is arguably the most important star in the universe, our sun, and the space weather has many of its origins in the sun and its variability. Of course, the center of the sun is a fusion furnace generating immense power, converting hydrogen to helium. energy that starts at the center here, maybe takes a couple 100,000 years to get out to the edge of what's called the radiative zone, about 2/3 of the way out the radius of the sun. The outer part's quite different. It's very different in character, and the outer part and the equatorial part especially rotate differently than the polar regions. And so there's this constant disruption that occurs in the outer layers of the sun, and is actually an efficient dynamo and generates powerful magnetic fields as well. When one looks in detail at the sun, it's changing on all sort of spatial and temporal scales, upwelling and downwelling of plasma. There are regions of emerging strong magnetic field called sunspots, and we'll talk more about that in the course of this. And the effects of that are quite profound. Looking at the sun more in X-rays, one can see powerful enhancement regions. There can also be large prominences. The Earth is maybe the size of one of these letters for NASA there, so it's huge in scale. And then the magnetic field changes significantly over the time of the sun's variability, about 11 years or so. It's actually a 22-year magnetic cycle on the sun. And then there are these blasts of material, which we'll talk much more about as well, called coronal mass ejections. And as we focus in on some of these bright regions in X-rays, these are areas of particularly intense magnetic activity. And when there are opposing magnetic fields there can be powerful solar flares. And of course, that's one of the prominent disruptions that we talk about in space weather. So the last 20 or so years have been a golden age for observing the sun. There have been observations of the sun in many different wavelengths and in many different ways. And with this understanding of the sun has become deeper and deeper over time with improving observations, both from the Earth perspective as well as other angles, you might say. Something fundamental for the discussion of space weather is the activity cycle for the sun. The sun is a main sequence, sort of a normal star, a magnetically active star. Can go from highly active, as seen in this image, taken about yearly intervals, to becoming much more quiescent, and then moving back to a much more active configuration. And we're right now moving toward this most active state again. So the sun is nearing its peak of activity. One measure of activity is to just look at the number of sunspots to sort of count the number of sunspots. That goes back 400 years or so for the first recognition of that. But here's from 1965 to the present time. The sort of daily variability is shown by the green here, more monthly averages. And then what you see is that indeed the sun goes through this activity cycle. And here we are now in October of 2024. The predictions had been that the sun would be not terribly active. It would be about the same level of activity as it was last peak in 2012 or so. But the sun has already violated that expectation, has been much more active. And some of you may have seen recent evidence of that with aurora here in Colorado and even further south than we are. And so removing a lot of the hash on this and just showing the sort of observed sunspot, smooth sunspots, it's very likely that this solar cycle we will be at least as active as the average over the entire sunspot history, and probably much higher. And so this is a larger and more active cycle than most experts had expected this cycle to be. Going back 2 cycles to this period, the comparable period in the solar cycle to 11-year cycles ago, the sun was extremely active in late October of 2003. These were the so-called Halloween storms. I can go back and play that again if you like. But powerful solar flares late in October. the blast of radiation, and then the snow that appears is really energetic particles from the sun, and then a coronal mass ejection that's headed right toward the Earth. And so this is the sort of most worrisome scenario for space weather when that kind of event occurs. So coronal mass ejections are expulsions from the sun of very large amounts of material, 10 billion tons or so of material, perhaps moving at 7 or 8 million miles an hour. And so a coronal mass ejection of this scale can reach the Earth in substantially less than a day, for example. And those are, again, difficult to deal with and difficult to predict. If the interplanetary field is of the appropriate orientation, energy can be very efficiently transferred from the solar wind into the Earth's magnetic envelope, the magnetosphere. That energy dissipated can reveal its presence by having strong interaction in the polar regions or even the mid-latitude regions. And so coronal mass ejections are one of the big worries for space weather events. As you're probably well aware, the near-Earth region is populated heavily by spacecraft. Just one example, there are over 600 spacecraft in the geostationary orbit. The spacecraft at that location appear to stay above a given point on the Earth's surface. And this is just the civilian communication satellites. And there's estimated to be several $100 billion of assets in space just in that region. If you look more broadly, there are, we have to change this each day, but there are 11,000 spacecraft in Earth orbit now, operating active spacecraft. If I'd given this talk a few months ago, that would have been about 7,000. So especially SpaceX is launching hundreds of spacecraft at a time into Earth orbit, and those Starlink spacecraft are having a very significant effect on radio astronomy, a significant effect on nighttime astronomy. And as I say, this leads to a whole nother conversation about how we're disrupting the near-Earth environment with putting more and more things into space, not to mention all the space debris that accompanies that kind of activity. So if we talk about the corpuscular radiation, the effects that has, there's of course the coronal mass ejection. Shock waves in front of the coronal mass ejections can be a very efficient place for accelerating particles to high energy. Those solar energetic particles are a major concern for both robotic activities in space and also for humans in space. Another component is one near and dear to my heart, which is the radiation belts around the Earth, the Van Allen radiation belts. And a third component is the galactic cosmic rays. This is a much more prevalent kind of thing all the time. Galactic cosmic rays are modulated by solar activity and anti-correlation with sunspot number, for example. But high energy galactic cosmic rays are always around and are a big concern for space weather as well. A long time ago, published a paper in Science about the effects of space weather on satellite operation. And this diagram shows some of those kinds of effects. But high energy protons or heavy ions from the sun can have very significant effects, can cause bit flips, and can change the state of electronics. A more obvious and visible effect of that is to see what it does to CCD cameras operating in space, for example. And this is a picture taken at the height of solar cycle, a couple of solar cycles ago. And just 6 or 7 hours later, this is a comparable picture. All the snow that's here is charged particles hitting the camera. It doesn't take a lot of imagination to think about a human eye or human brain in space being hit by that, just that sheer intensity of charged particles. The effect on, another effect prominently associated with the Van Allen radiation belts is deep dielectric charging, high energy electrons that can penetrate dielectric materials bury themselves and can lead to discharges. Ordinarily, if there's a low intensity of energetic electrons, they come into an insulator, they leak away, and there's not too much problem. But for intense events that can build up and have essentially a small kind of lightning discharge in space, and that has been demonstrated time and again to have a very significant effect on electronics. And it has many times caused either temporary or even a total failure of satellite systems when the deep dielectric charging phenomenon has been worrisome for a very long time. Because of those worries about the radiation regions around the Earth, NASA undertook a mission started in 2005, I guess, with the announcement of Opportunity. This spacecraft combination, dual spacecraft, originally called the Radiation Belt Storm Probes, renamed the Van Allen probes, launched in 2012. We were very pleased and proud to be part of that at LASP. Having instrumentation of several sorts, but the one that I was most involved in was the relativistic electron-proton telescope. That made several discoveries, including the fact that the textbooks had always said there were two radiation belts, the inner belt made up primarily of high-energy ions, and the outer belt made up of electrons. We actually found that quite often there was a third belt, so there were three Van Allen belts, not two. If we look down on top of the Earth and the region around and look at the orbits, they were in elliptical orbits about going out to about 6 Earth radii, a 9-hour orbit around the Earth, making measurements all along that trajectory. If we just recognize that the particles drift around the Earth in the magnetic field much faster than the spacecraft move, one can make these measurements and actually make a map of the radiation. So imagine you're looking down on top of a torus or a donut and cutting through. You're getting sort of a weather map, a space weather map. And over time then, we can watch just how rapidly and profoundly the energetic particles, these are 4.5 MeV electrons, very high energy electrons, changing on a daily and sub-daily timescale. And you can see the populations forming, disappearing, going down to virtually nothing, having this inner belt, sometimes seeing the multiple belts. And it's really quite fascinating over the, I guess, 9-year lifetime of the Van Allen probes to be able to watch that evolution constantly over many, many different external driving conditions. So just to drive home the point, we've been using space much more in many ways that might not have been imagined decades ago. But now we know that there are many users, and I'll talk more about this, of the GPS or other GNSS systems. The air transportation system is using a space segment. Increased vulnerability of the power grid is a real concern. I'll talk about that. The commercial satellite industry that I mentioned briefly before. Exploration of the moon and beyond. Certainly there's a strong concern about space weather in that regard. Broader aspects, space tourism and so forth, and Arctic economic development are just a sampling of the things that one is concerned about. Back in the mid part of the last decade, there were assessments about GPS usage. At that time, the business associated with GPS was a bit over $10 billion. It was estimated that it was going to develop rapidly, and that's been borne out now. Today, the use of GPS for economic purposes of various sorts totals about $1.5 trillion worth of business in the US alone. And GPS is with us everywhere in the usual of navigating your car and things and boats and stuff, but the positioning is, in many ways, is dwarfed by many of the other uses to which GPS is put. And this also includes attempts to use it for broader purposes like the airline industry And the idea was to get away from using just ground transmitters to help airplanes, but to allow more precise positioning and knowledge of position for commercial aircraft using the GPS signals. And that's fine during normal circumstances, but if we go back to the Halloween storm period in 2003, here blue is good, red is bad. This is the total electron content in the ionosphere. And over the course of this developing storm, the entire region above North America was made basically unusable for the GPS system, and this persisted for about 30 hours. And so this can have very significant consequences. What can happen with GPS is ranging errors and just scintillations in the ionosphere that are caused by particles from the sun, activity from the sun, disrupting the nearest system. And when that happens, the ranging errors can make it very difficult to maintain the kind of precise ranging and position knowledge that's really necessary. This can also affect, of course, many other things, precision agriculture, navigation at sea, and so forth. Another effect of space weather that's quite important is a solar flare occurring on the sun can cause changes in the ionosphere, which in turn can affect what bands of high frequency and very high frequency radio communication can be used. And so we're at a time now where solar flares of great power are occurring quite frequently, and this kind of changes in the availability of HF radio communication for airlines and other uses is really quite significant. It's not so prevalent now as better satellite communication systems come in, but for quite a period of time, as there started to be many, many more flights of airlines over the transpolar routes, the requirements for United and other airlines was to remain in continuous high-frequency radio communication with the planes. And when there's a powerful storm, I'll go back to my favorite storm period in late October of 2003. I hope you can see this, but because of solar energetic particles funneling along the magnetic field down into the polar region, the entire north polar cap region was made unusable for radio communication. And so under those kind of circumstances, even more modest storm periods, the airlines have to fly low latitude routes and not fly over into these sort of radio dead zones over the poles. And this can cost substantial amounts more money and delays in flights and so forth. And of course, there's human space flight and the International Space Station and extravehicular activity there's a major concern about solar particles and the effects that they can have on humans. And that becomes even more prevalent as one goes beyond the sort of protective envelope of the Earth's magnetic field. Going to the moon and out to Mars and so on would be a whole host of new kinds of issues. I was privileged, I guess I'd say, to chair a National Academy study looking at the space radiation hazards and how's that related to the vision for space exploration as it was envisioned back in early this century. And that report listed some of the consequences for radiation risks associated with space weather and carcinogenic effects, degenerative effects, damage to the central nervous system, acute risks. I've always noted that death is a bad acute risk. But vomiting in a spacesuit, if you're out on the surface of the moon and away from a place where you can get out of your spacesuit and you became ill and started vomiting, that could be a deadly consequence. And so the people who are now involved in the Artemis program are very concerned about space radiation and its effects, short-term and long-term. In 2007 or so, I was at a space weather meeting here in Boulder, and there were representatives from national security side and civil side and so on. And I just read a report about the effects of, or the hazards associated with flooding and the costs of that, economic costs of that. And I noted that there were really no good studies of what the economic and societal impacts of severe space weather were that were comparable to that. And so no good deed goes unpunished. So I was asked to chair a study to look at the economic impacts of severe space weather. We had about 80 attendees from academia, from industry, from government, and from the industry associations. And that study has proven to be quite long-lasting in its effects, I'm pleased to say. And at the meeting, Department of Homeland Security, I think, was the one that put this slide together. But if you think about just one sector, the electric power system, and you think about what consequences are of losing power, I think we've all experienced brief power outages, maybe an hour or a few hours. Maybe even some have experienced power outages for a few days. But when you start to think about power outages last weeks or months or possibly years, it becomes quite staggering. And losing power, electric power, bulk power, means that you can rapidly lose the ability to pump fuels, pump water, potable water. You can lose transportation capabilities, maybe lose emergency services, losing phone contact and so forth. Longer term effects on banking and finance. It's really a staggering interconnectivity for one thing cascading to affect many things. In this report, we showed some of the work that had gone on modeling a large space weather event, a large solar storm, and the effect that might have on the extremely high voltage backbone for the power grid in North America. And the analyses that had been done there could be that each of these red and green dots just indicate how much induced current, ground-induced current there is in the various large transformers. And the conclusion was that under the worst circumstances that one could lose dozens or perhaps hundreds of transformers due to burnout of the transformers. And the electric power grid is increasingly vulnerable to these kinds of effects. And the transformers that are worried about here are not the small ones that you might see in someone's backyard or something, but would really be house-sized kind of transformers, very expensive, and you can't go to Home Depot and pick one up. You really have to build those specially. And so the consequences for this have been looked at from many points of view by many different people in the industry, in the insurance industry, for example, and have all concluded that the consequences could be quite severe. The event that's often pointed to as the worst event, which it probably wasn't and isn't, but it was an event that occurred in 1859. There was a white light flare, the first observation by Richard Carrington of a white light flare. Shortly thereafter, there were very powerful aurora. Aurora extended down to very low latitudes, down to India and to Cuba. The effects on the internet of that age, the telegraph system in North America, severely affected. There were fires that broke out due to discharges occurring, induced currents in the telegraph wires and so on. People could actually read newspaper print by auroral light in the northeast, for example. And so this is a very impressive, actually, pair of powerful events, and it's been held up as the example of what could happen in the present day. As historians, I suppose you could say, of science have looked more carefully, there have actually been a number of storms in the intervening time between then and now. This isn't something that occurs just every 150 years or so. It's probably a much more frequent occurrence than that. But a CME can produce geomagnetic disturbances, which can produce these induced currents in long wires, the backbone of the power grid, as I mentioned, in pipelines and other conductors. And those consequences can be quite severe. This garish slide talks about the damages extending into the trillions of dollars. There's, there are debates about what's the right number to attach to this, but again, many different independent bodies have estimated that power outages lasting substantial periods of time, weeks or months, could run into a very huge cost. Now you could say, okay, 150 years ago, so what? It's not going to occur soon. But in the last solar cycle, which, as I mentioned, was a relatively modest one, the sun became active in the summer of 2012. There was a very complex and large sunspot group that occurred. There were fairly significant coronal mass ejections and X-class flares that occurred associated with this. This is on the 12th of July, and that's when this was facing the earthward direction. About 10 days later, as the sun had rotated, this active region had moved out of sight, more or less, of the Earth, but was in direct view of a NASA satellite called Stereo A. And this is the sun here, of course. This is the active region we're talking about. This is the coronagraphs that show the activity. And so you see this flare go off, coronal mass ejection heading right toward Stereo A, and the effects, including the charged particles that we've talked about before. So what if this had happened 10 days earlier and the Earth had been in the line of fire? Or what if Earth had been where Stereo A is? This is the kind of ugly mess of magnetic field that caused all this. So this is one example of the modeling that's gone on. A lot of this was done here in Boulder with Dusan Adrasil and others. But in this picture, we're looking down on top of the inner solar system. The Earth is here. And this blast that's going out directly toward this Stereo A spacecraft, which is at 1 AU, the same distance as the sun is from the Earth. But the spacecraft was in a propitious location and was hit directly by this coronal mass ejection moving out from the sun at very high speed. So in about 18 and a half hours, it went from the sun out to the Earth orbit. So we had the benefit here of having measurements from Stereo, as we might have in the along the Sun-Earth line under other circumstances. But Stereo was making measurements of the magnetic field, of the solar wind speed, solar wind density, and we were able to take, in this study published in the Journal of Space Weather, we were able to take these kind of measured conditions in the interplanetary medium, run them through our models, and predict what the effect would have been as far as a strength of a storm if that had been directed toward the Earth. The largest storm that's been recorded in the 20th century was 589 in these nanotesla units for this index DST. I won't go into the details of that other than it's an agreed upon measure of strength of geomagnetic storms. The storm associated with that July 2012 event would have been easily twice the size of the largest storm that has occurred. The large storm produced a major power outage throughout the Northeast and in Canada in 1989, and this storm would have probably caused a lot more damage than that. So this is some other researchers who looked at the same thing and concluded rather similarly. I can stop and take a little bit of a breath since this plays out sort of slowly, but it makes some points that this active region is going along, popping off coronal mass ejections as it goes. Again, this is the same kind of picture, Earth, stereo A over here. There's a pretty substantial coronal mass ejection that came out. It moved comparatively slowly, but it cleared out much of the inner solar system, if you will, just changed the plasma properties quite considerably. And then along came the next one, and you'll see the trace over here. The next coronal mass ejection was much larger, much more powerful, moved out much more rapidly, and there were essentially no impediments to it, and that's probably why there was such a very strong interplanetary southward field and so forth. So getting to a further point here, that large geomagnetic storms are a great concern for space weather. And one might think that the biggest worry would be when you have the strongest solar activity cycles. But looking back at the record back into the 1700s, you can see that there have been a lot of strong activity events, cycles, and strong peaks in sunspot number. But the Carrington event of 1859 was during a relatively weak sunspot cycle, and the 21 storm that was studied also less than average. And so it's not just a given that you have to have an extremely large sunspot number cycle to necessarily have very large and significant space weather events. Another privilege, I guess, was to chair the decadal survey, the studies that are required for NASA divisions, and this is for solar and space physics. This came out in 2013. In this study, in this report, we had a chapter dealing with how to enable effective space weather and climate capability predictions. One of the things we noted was that much of what the improvements that have been occurring in space weather prediction had been built on the back of scientific satellites from NASA. The ACE spacecraft is about 30 years old now. SOHO's not too far behind. SDO's maybe approaching 20 years old. The radiation belt storm probes have ceased to operate. And so these NASA capabilities, which were very beneficial for space weather, have been are aging out, and by no means are they required to operate 24 hours a day, 7 days a week. And so this is really not the way to have an operational space weather system. And so I think we need clearly to have better eyes in the sky in order to do an effective job of space weather forecasting. So instead of this kind of thing, a study that was led by the Applied Physics Laboratory at Johns Hopkins looked at what is really needed in order to have effective prediction, effective forecasting of space weather. And this includes observations, of course, at the L1 point, about a half an hour's flight time upstream of the Earth, but also to have measurements at other Lagrange points, L1, L4, and L5, in order to get a more three-dimensional view of the sun, to actually have spacecraft that go to higher latitudes over the sun and can really look at the key magnetic fields at the higher latitude portions of the sun. And we have measurements at L1, but virtually none of the rest of these things that are really required. In the decadal survey, we urge strongly that NASA or NOAA or some combination should be investing like $100 million per year just to increase this observational capability, and that really hasn't happened much at all. We also urge that there be better modeling to use the information we do have. I'm pleased to say that CU has initiated, or did initiate in 2017 or so, 2018, a center devoted to space weather, the Space Weather Technology Research and Education Center, Space Weather TREC. This is headed by Tom Berger, and LASP, my institute, and the Aerospace Engineering Department and so on have been cooperating quite substantially to improve many aspects of space weather, but certainly focusing on improved modeling. And just a short while ago, within the last year or so, we've been selected by NASA for a center of excellence for transitioning space weather from research more toward operational kind of capability. Not all the way to operations, but moving it along toward that. The center here at CU, again headed by Tom Berger, is called the Space Weather Operational Readiness Development Center, and it has as the goal, a principal goal, to improve models, especially in the near Earth region, where, you know, closer to the photosphere, as I like to say. So what is the space weather scorecard, forecast scorecard? I think we can say with some confidence the sun will come up tomorrow. The sun will continue burning hydrogen for probably another 5 billion years, so I wouldn't worry too much about that aspect. The sun will be there. But the sunspot cycle will be about 11 years or so. It's as short as 9 years, maybe as long as 14 years or something, but approximately. So we know that that's pretty reliable. But as I've tried to show you, the size of the sunspot cycle is by no means well understood or predictable. So I'd say that's a big no. Solar flare onset, if we wanted to predict solar flares with precision of seconds or minutes, no way, even hours or possibly even days, that's not so good. If we see coronal mass ejections, if we have eyes on the sun and can see coronal mass ejections starting out from the sun, we have some time, and moving out at the typical speeds for coronal mass ejections, we can sort of say yes, that it's going to hit the Earth or not. And so that's encouraging, and that work has been productive. But the big unknown is whether the interplanetary magnetic field is pointed in a southward direction opposite to the Earth's magnetic field, whether it'll be geoeffective or not. And I think we're still far away from being able to say that with confidence when the coronal mass ejection starts out from the sun. So that's a big no. And hence we can't say whether a geostorm will be a dud or will be a really significant space weather event. So I think that's no. And so are we ready for the big one? Not really. I don't think we are. So how do we solve the space weather puzzle? Well, we need the better observations that I mentioned, and these need to be truly operational, 24/7, no kidding, really looking and having the data continually. To have the improved modeling that will accompany that, I think can go a long ways. And the net result can be a much improved forecasting. And one other thing I think that's been important over the last 10 or 15 years has been improved understanding from policymakers about the risk that space weather actually represents for society. And we've been trying to get the message out. There have been a number of excellent articles, more accessible to the policymakers and to the general public. One that came out recently in February was by Catherine Schultz from the New Yorker, and I commend this article to you. It's, I think, very well written and talks about the consequences of space weather in very accessible terms. So to summarize, I would say that the challenges of space weather affect all developed and developing countries. It's relevant both for civilian and military national security systems. I would characterize this work as basic research with a high public purpose. I think it goes back to the duality I was talking about before. As we understand more about the sun, as we understand more about the interplanetary medium, we can apply that and transfer research to operations. And I think future exploration, robotic and human exploration, will require much deeper understanding of the effects of space weather, and I think that is a very crucial thing. But finally, let me say that how do we adequately convey and appropriately convey the threats that space weather represent without being unduly sensationalist. I think I told Catherine Schultz we should be duly sensationalist, not unduly sensationalist. But you know, avoiding this Chicken Little syndrome, the sky is falling. Well, one positive about all this is that space weather has risen, I think, in the eyes of policymakers from obscurity to sort of the similar levels of understanding that we have about severe floods, about earthquakes, about hurricanes, and things like that. And so, and many of the things that we would do to deal with severe space weather are the same things that we would do to deal with any of these hazards of preparedness. But as you can see, space weather often could be of continental scale rather than local scale. So with that, let me say thank you, and I'd be happy to answer any questions. Thank you. You're the boss, okay?
Microphone. Let's start on this side.
You talked about detecting and giving some warning, but what about hardening of the key electrical grid systems, navigation systems?
Yeah.
I mean, I know the FAA has maintained ground-based navigation systems for aircraft
Just as backup.
as backup, so that we don't have to depend on GPS.
Yeah.
And what are the other most critical industries and infrastructure that we need to harden?
Yeah, thanks, Paula. There have actually, it's been encouraging over the last years that this raising of consciousness has also led to political action. For example, thanks to the efforts of many in the Colorado delegation, Senator Gardner, for example, and Congressman Perlmutter, sort of drove through the Pro-SWIFT Act, which is a congressional mandated that the industries that are affected have to show their plans for mitigating or hardening their systems and so on. And so I think that progress has been made there. The trouble is that these systems are of varying age and varying capabilities to withstand the effects. And so on some of the transformers that are on the system are 40 or 50 years old. So I think there's still quite a bit of concern, but the consciousness has been raised. There are things that can be done. Engineering around the problem would be great. Protecting everything that can be affected by space weather is unlikely, but going to the core things, you know, making an assessment by policymakers of what are the most essential elements that need to really be protected or rapidly replaced or something like that. And that's still a work in progress, but a very important component. Again, these millions of dollar kind of transformers, just, you know, as I say, putting a lot of those at the local Home Depot, just in case there's a storm, hasn't occurred. It's probably not likely to occur, but a lot of these transformers were actually not even built in the U.S., so that we didn't even control the supply of those. I think more of that's being done to assure that we at least have the capability of rapidly rebuilding some of the capabilities. Yeah. Good question.
Yeah, it's a very interesting talk. So at the beginning you mentioned you're just talking about space weather, but there's separate anthropogenic kind of space weather. Are there things people can control or mitigate these space weathers in case they know it's going to come, other than shutting off our devices? What else can we do about it?
Yeah, I'll tell you a brief story. After one of these articles came out about space weather, a woman in France sent me an email, and she said in the address line, said, "I admire your work." So I actually read the email, and in it she said that she had talked to the emergency preparedness people in France. She asked what should I do in case there's a severe space weather event. They said, get a large chocolate cake, eat it, and wait for the world to end. And I didn't think that was particularly good advice then nor now. But, you know, as I mentioned, doing many of the same things as an individual, some of the same things that you might do in preparation if you lived in a flood-prone region or if you lived in a hurricane-prone region, would be to have, a generator to make sure you had supplies of water and so forth, so that you could really weather the storm for an extended period of time, several weeks perhaps, something like that. As far as more broad preparation, I would say that, again, I think we just have to harden a lot of the systems that we presently assume are going to be there. But I think we could lose communication over a broad region. We could lose availability of fuel and a lot of those things. I think we have to think more systematically about that.
I admire your work.
Thank you. I'll read your email.
I work on machine learning research for space weather forecasting.
Mm-hmm.
So my question is, do you think we have enough high quality data to create accurate machine learning models, or do you think we need more or better instrumentation to get the whole picture and start predicting forecasting like that?
Well, you can probably say better than me, but I think we haven't very fully exploited the data that we now have, and I think the kind of work you're doing is great. We started things that were not called machine learning necessarily many years ago. That work was criticized. Well, you're not doing first principles physics models. You're not learning. You're not getting a deeper understanding of what causes all of this. So you people shouldn't even be funded to do this. But those empirical models work damn well, I would say, and that's something that now is more fashionable, more accepted. And I believe there's a tremendous amount lurking in just the data we have. But I would say that it's going to help us uncover where the real gaps are and where the holes are and where we need more information. So how's that for a Weasley answer? Good.
Yeah, so just to add on to his question, I've been working on a satellite that does X-ray spectroscopy of the sun. And I've been looking for what are the new development directions for payloads for various sun measurement systems. And did we find any a principal component analysis for these set of sensors and this spectrum will be helpful for predicting space weather?
Well, I think those are all forefront things that people are indeed working on. I don't think we've gotten a major breakthrough in those, in those realms. We haven't found the magic part of certain wavelengths of the sun to look at, or certain kind of features that haven't been measured well in the past. But I have great hope that as we bring more, say, CubeSats and smaller things on board, that when we've had to rely on the Battlestar Galacticas, and that come online every 15 or 20 years, nobody's really got the confidence to try new things there. But I think with a lot of things, in fact, that we're doing here at CU and at LASP, for example, I think we're going to find out a lot more and get a much better shot at more effective forecasts, understanding the keys to better forecasts. I hope that answers your question. Yeah.
Yeah, I don't work on space weather. However,
you were at lunch.
I was at lunch, that's true. I had a question about, you mentioned, we need maybe some more satellites to characterize these flares up, in the sense of hours and days and this kind of thing. Is it just a quantity kind of thing? Do we just need more things out there? Or is there also a kind of qualitative sensor kind of upgrade we can do to better characterize the behavior of the sun?
Yeah, those are good questions. I think it's first, it's a point of view thing. Making sure that we're seeing the whole system and not just through a soda straw. And one of the really absent things is having a good view of the higher latitude parts of the sun. Those are the magnetic fields that really come down and hit us at 1 AU. So that's a key importance. But having more continuous observations is another thing I mentioned that we really need to. We can't just be taking a snapshot here or there and think that we're really putting together a systematic picture. So, good question. I enjoyed the lunch conversation too.
Okay, Dan, I've been a practitioner of space weather prediction for the past 17 years at the Space Weather Prediction Center, and I got to say, first of all, you nailed it. I mean, everything that I would like you to know, he said. So
well, thank you.
Yeah, that was awesome. I'll put in a plug for empirical models just because I came out of the meteorological community, And, a lot of that was our bread and butter, especially when, I started out in the 80s. The numerical models were good, but they weren't nearly as good as they are today. And we relied heavily on that stuff.
That's right.
And it helped us make better forecasts. And it makes me sad when I hear the stories like you told where, that's not real. Well, I need it. I give them money. So, but that's one thing I want to talk about.
I'm glad to hear you say that. And I would say that I love physics. I love equations. I love first principles models. But if something works, let's use it, and let's utilize every arrow in the quiver. Not just say that we have to be purists and start with the nuclear furnace in the center of the sun and predict everything on every time scale. It's not going to happen. So, thank you.
Well, I would like to bring the colloquium to its close. Thank you, Dan.
Thank you. Thank you, Mihaly.